Okay, in this video we want to look at how we can add and subtract vectors using equations as well as the geometric approach that we have been looking at. So let's look at a vector addition in general. We've already seen that we have a vector A and a vector B. If we want to add them together, we can simply use the tail to tip twice method. So I've got my vector A here, and I have my vector B. I've connected the tail of B to the tip of A, and that lets me draw my vector sum A plus B. And we want to look at how we can add these together with an equation. So let's consider the x component of A, which would be the part of vector A that is along the x-axis. And we, of course, would have a y component of A that would be vertical, and you would say that the AX plus the AY would be the vector A, tail to tip twice, but we're looking at just at the A component of X, and then we're going to look at the A component of B, which would be from there to there. You could imagine a line going like that for BX, and then a line going up for BY, but if I have this as my BX, I can scoot it down here, and I can see that AX and BX are connected tail to tip. So if I go from there all the way to the end of BX, that would be AX plus BX, but look at what that is. That's equal to RX, where RX would be the X component of the sum, which would go down there. So this basically tells us how to do vector addition using the vector components. If I have a vector that is a sum of two other vectors, so in this case I've got A plus B equals to R, I can write each vector in terms of its x and y components, AX and BX, and then I would also have an AY and a BY. I haven't drawn AY and BY into the picture because that would make the picture very cluttered, but I think you can see how that would work. And my sum vector is going to have a component Rx such that Rx equals AX plus BX. And that's what I've written over here, Rx equals AX plus BX. And notice I've got little vector symbols up here, but both of these vectors point along the x-axis. So I can write them in terms of the unit vector x hat. And so my Rx vector would be AX magnitude plus BX magnitude in the x hat direction. And if I want just the magnitude, that would be the part in the parentheses, so the magnitude of Rx is equal to AX plus BX. And similarly, the magnitude of RY, which would be everything vertical, that would be AY plus BY. In other words, if you want to add up two vectors algebraically, you just add their components. You add their x components together and get a total x component for your answer. Then you add the y components together and get a total y component for your answer. Now let's look at an example. Just for fun, I'm going to use a different convention. I often like to use the x hat and y hat to represent the unit vectors along the x-axis and y-axis, but there's an older convention I talked about in a previous video. You can also use I hat and j hat, and just so that you can see one with that, I'm going to do that in my example. And so I've got two vectors defined here. A is 3 in the I hat direction, or along the x-axis, minus 2 in the j hat direction. So that would mean 2 units in the minus j hat direction. Then here I would have B is equal to minus 6 I hat. So that means 6 units in the minus I hat direction, and then 3 units in the minus j hat direction. So the problem is to first draw A and B, and then draw C such that C is the sum A plus B. Then we want to determine that sum C equals to A plus B algebraically and compare it to the drawing. Here's a hint, the two should match. And then finally, we want to figure out what is the magnitude of the vector C, which is of course A plus B. What's the magnitude of A plus B? And what angle does the vector C make with the x-axis? So this is our task. And so we're going to look at adding these two vectors geometrically, and we're going to add them together algebraically, and then we'll compare those two approaches and see that they match. Okay, here is our first task. We want to draw the vector A, we want to draw the vector B, and we want to draw the vector C, which is equal to A plus B. So let's draw A first. We're given that A is equal to 3i hat minus 2j hat. That means 3 units, 1, 2, 3, along the x-axis, and then 2 units down along the negative y-axis, 1, 2. And so you can see I've drawn my vector A to the point 3, negative 2, because it's 3 over to the right and then 2 down. My B vector is minus 6i minus 3j. So that's minus 1, 2, 3, 4, 5, 6. That's 6 in the negative x direction. And then minus 3j, that's 1, 2, 3 down. And so that's going to point to the point negative 6, negative 3. And that's our B vector. Now, in order to get the sum, I've already got these connected tail to tail. I could redraw my B vector up here and do tail to tip twice, but since I've already got them connected tail to tail, I'm just going to do the parallelogram method. So I'm going to extend the line parallel to A from the tip of B. I'm going to extend the line parallel to B from the tip of A, this yellow line here. Where they cross, that's where the parallelogram is formed by the vectors A and B. And so the diagonal of that parallelogram is C. Now we can read the value of C right off the graph, because C, if I go up to the x-axis, is 1, 2, 3 over. So it's 1, 2, 3 in the negative x direction, so that's going to be negative 3. And then it's 1, 2, 3, 4, 5 down. So if I look at where I've written my C solution here, I've got minus 3i hat, so that's minus 3, or 3 in the negative I hat, or 3 in the negative x direction, minus 5j. So that means 3 to the left, 5 down. That's basically what that tells you to do. Negative I hat, negative j hat. Okay, so now we can do an algebraic sum. We can add up using algebraic equations. So we have our C equals A plus B, where we saw previously that A was 3i hat minus 2j hat, and that B was minus 6i hat minus 3j hat. And so we want to group all the like terms. We want to get all the x parts and all the y parts together, or all the I hat terms together and all the j hat terms together. So 3i hat minus 6i hat, those are all pointing in the x-axis along either the x-axis, positive or negative. So we just add those numbers, and we can factor out the I hat. So 3 minus 6 I hat, I factored out the I hat. Up here I've got minus 2 minus 3 j hat. I can factor out the j hat. And so that leaves me with C is minus 3 I hat minus 5 j hat. And that's exactly what we got from doing the vector addition graphically. So it's comforting that the two methods give the same answer. Now we have our answer, C is equal to minus 3i hat minus 5j hat. Now I generally recommend that once you get to the point where you have your answer that you've done algebraically, it's generally a good idea to sketch it. And you don't have to be super careful. You don't have to get out your ruler and protractor, but just kind of eyeball it. There's 1, 2, 3 in the negative direction, 1, 2, 3, 4, 5 in the negative direction in the y. And so my vector is going to be something like this. And that's going to be my C vector. Now what I can do is I can sketch in my x component and my y component. And I know that this is 3, and I know that that's 5. And now I've got a triangle that I can do trig on. And so if this is some angle theta here, I can say that the value of my C vector here in blue, that's going to be, it's going to have a magnitude of 3 squared plus 5 squared. That's just from the Pythagorean theorem. Now, I was careful when I wrote that out here. I said it's minus 3 quantity squared plus minus 5, because technically that's a minus 3 and that's a minus 5. But what happens when you square a negative number? it goes away. So if you just put 3 and 5 there without the minus signs, it might be a little bit sloppy, but I don't care. You get the right answer. And so if you do that calculation, you get the magnitude of C is 5.8 units, whatever your units are. And your angle is simply the arctangent of the opposite over the adjacent. And so you see theta in the picture, and so the opposite would be 5, the adjacent would be 3, and I recommend very strongly that you avoid putting any minus signs in your arctangent. Here they would cancel, so it wouldn't really matter, but there are situations where if you put negative signs in, it can give you misleading answers, confusing answers. If you always put the positive numbers here, you'll always get the number that corresponds to the triangle that you've drawn. So as long as you draw a picture and you label the angle that you're talking about, it's unambiguous what angle you are using. And that's very important because ambiguity leads to confusion. So I recommend very strongly that you should always draw the picture, draw your triangle, show what your components and your hypotenuse are, show what your angle is, and then you're good to go. Now we want to look at an example of calculating a vector difference, and we can use 2 different methods for doing this. One, we can add a negative vector, and personally I think that approach is easier to understand, but it's less useful. The other approach is the triangle method for vector subtraction, and it's more useful, but it's a little bit more difficult and it's easy to make a mistake. So I would suggest that you learn both because both are going to be useful for us. It turns out that the triangle method is actually the one that we're going to be using the most, but learning the other method at the worst case scenario gives you a check to make sure that you've done everything correctly with the triangle method. So here we're going to look at vector subtraction, and we're going to look at the first method of calculating a vector difference. We're going to use the adding a negative method. In other words, if I want to form the vector difference a minus b, that's equal to the vector a plus the vector minus b. And remember what that means. If you have a vector minus b, that just means that you flipped your b. So let's look at doing this, and we're going to superimpose it on our xy coordinate system again just for fun. So I have my a vector and my b vector that I used before, and I want to form the vector difference d equals a minus b. So the first thing I want to do is flip b 180 degrees. So I'm going to keep them at the origin, but now I've flipped b 180 degrees. Why did I do that? Because I want to add negative b to a. And so by flipping it 180 degrees, I've formed negative b. And so now I simply need to add these 2 vectors together, a and b, and that'll give me my vector difference. Again, I can use my parallelogram method. I could have started my b vector here and drawn, tail to tip twice, and this would be my b vector. And I just made a mistake. I made it on purpose. Do you see what my mistake is? That's not actually the b vector. Which vector is that? That's actually negative b. That's a very common mistake that my students make, though. So you want to make sure that you don't do that. Always make sure your vectors are labeled properly. And so regardless of whether I'm doing tail to tip twice or whether I'm doing the parallelogram method, drawing the diagonal of the parallelogram, this is what gives me my vector sum of a plus negative b. And so this pink vector here is a plus negative b, and I can read that directly off the graph, 1, 2, 3, 4, 5, 6, 7, 8, 9 in the I hat direction, and then it's up 1 in the j hat direction. So graphically, we've been able to add these vectors using what we know about vector addition, and because we're adding this negative vector, we're actually doing vector subtraction, which is kind of cool. Now I want to show you an alternate approach for doing vector subtraction. You can do what's called the triangle method, and in this approach you connect the vectors tail to tail. Now here's a caveat. you do not flip the second vector. You absolutely do not flip any vectors when doing the triangle method. You use the original vectors. So you take the original vectors, you connect them tail to tail, and then you draw the vector difference from the tip of the second vector. That would be the one after the minus sign. So if I want to do A minus B, I would call B the second vector and A the first vector, because B is after the minus sign, it's the second one. And then I'm going to draw from the tip of B to the tip of A, from the tip of the second vector to the tip of the first vector. So here is my vector difference with the triangle method. I have drawn my A and B, and this again is not negative B, this is my original B vector, and I'm going from the tip of B to the tip of A. I've got them connected tail to tail here. I go from the tip of B to the tip of A, and that is 9 over and 1 up, and that's exactly what I got using the other method. So let's look at doing it algebraically. Basically, we want to know if we want to do any kind of addition with components, we simply group together the same component types and add them like regular numbers. In other words, we're going to group all the I hat terms together and all the j hat terms together. Now let's look at what we have. We've got A minus B, that's 3I hat minus 2j hat minus, in parentheses, minus 6I hat minus 3j hat. Now, the first thing that I would do is distribute this minus sign here. Minus times a negative becomes positive. Minus times this negative makes that positive. So I can rewrite this equation down below as 3I hat minus 2j hat plus 6I hat plus 3j hat. Now I can group the I hat terms together. I get 3I hat plus 6I hat. I can group the j hat together, the j hat terms together. That gives me minus 2j hat plus 3j hat. Now I can simplify, and algebraically I see that I get that my d vector is equal to 9I hat plus 1j hat, or I can write it normally as just simply 9I hat plus j hat, and that's the answer that we got with the two different graphical approaches for vector subtraction. So it's very comforting to see that all these things work the way they're supposed to. And so now you see how to add vectors algebraically and graphically. You see how to subtract vectors algebraically and graphically. And you'll have a chance to practice these on your homework very soon.